Yeah, hi everyone. My name is Mattia Serra, and I'd like to thank the organizers for giving me an opportunity to speak here. For those of you who don't know me, I have a group in physics at the Department of Physics at UC San Diego, and we are interested in nonlinear dynamics and modeling of living systems or active matter. Specifically, we develop methods to identify patterns in nonlinear systems, also when you don't know the equations, for instance, from data. And then we try to develop also mechanistic models to predict their self-organization. Today I want to talk about a project which is called Morphogenesis-Mediated Morphogen Transport. If you don't know anything about morphogenesis or you don't care about morphogenesis, it doesn't matter, because it's going to be a general mathematical framework, and an alternative title could be Pattern Formation in Motile Environments. Okay? And this is joint work with Alex Plum, who is a PhD student in the group. So, embryogenesis entails the development of function and form in a very synchronized way. So cells have to specify to acquire a particular fate or function. And then some particular cells usually drive tissue flows. They generate active forces. This is close to what we heard from Fridjof and other talks earlier. And then these cells that generate active forces generate flows. This is basically a chick embryo that is undergoing large-scale motion at the embryo scale, basically. And another very important aspect of this process is patterning. Okay, so patterning is the evolution of molecules, which we call morphogens, that will basically give cells orientation, so where they are in the embryo, and they will allow cells to communicate with each other. And today, despite we did work in a few of these aspects, today I want to focus on the interplay between flows and patterning. Okay? And especially because if we look at pattern formation paradigms, they were mainly developed for static tissues. So if you look at Turing systems, usually the advection term is not there. And also, when cells interpret patterns as they move, it's very important that you're actually looking at in the cell frame rather than the fixed Eulerian frame. And there is basically a growing body of literature that understood basically that when you have, for instance, tissues sliding with each other, the cell-cell signaling or intercellular signaling between these two blobs will depend on this basically relative motion, and that will eventually affect also the differentiation of cells. So what we need apparently is a patterning framework for motile cell environments. And this is actually even more important in the context of early development, because the flows are not just isotropic growth or shear, but they're very spatiotemporal complex across model systems. And the idea is that we want to try to address a little bit in this talk is how do complex tissue flows affect patterning. And to do that, I will do it in two parts. So in the first part, I will propose a method to compress or simplify spatiotemporal velocities, let's say the ones that you can actually look in a microscope, and transform spatiotemporal flows of cells. Let's say this is basically an embryo with several thousands of cells that move into units, which we call kinematic units, which could be attractors and repellers. And we're going to do it basically using the Cauchy-Green tensor. I'm going to go into the detail of this. And this is the first part of compressing morphogenetic flows. And in the second part, we'll rewrite the advection reaction diffusion equation in Lagrangian coordinate, which is the coordinate that moves with the cell. And we will see basically that the Cauchy-Green that we used here pops up naturally as the effective diffusivity in the cell frame. So we're going to discover that, and also a very natural connection that connects attractors and repellers in position with barriers and enhancers of diffusive transport. Okay, and then we'll close with a simple notion of embryological light cones, which does the following. If these cells are moving, they are basically moving in a very high motile environment, and you say these cells start secreting a particular morphogen, what are the cells that after time t can be reached by this morphogen, removing the confounding effect of motion. Okay? Before I go into this first part, I want to just maybe make sure that we are clear on Eulerian versus Lagrangian coordinates. So Eulerian coordinates, they are fixed and don't move with cells, while Lagrangian coordinates, they co-move with cells. Basically, x is the classical Eulerian coordinate, x0 is a Lagrangian coordinate. You can think of a label or a number for each tissue patch or cell, and this coordinate will remember all the path of this cell over time. Okay? And whenever you have Lagrangian description or any quantity in Lagrangian description, you can describe it at the initial configuration or at the final configuration, depending on your convenience. So I'll give you an example. If there is a morphogen distribution, C bar of xt, this is the evolution of this morphogen in the Eulerian frame. That's basically its geometry. But now imagine 3 cells that are moving within this dynamic morphogen distribution, and the value that these cells will be filling are precisely C of xi, x0i, comma t. And this Lagrangian description is precisely what's important for cells to take decisions, because this is what the cell is feeling as they move. Okay, so let's go into the first part. The first part is trying to understand if someone gives us a velocity field like this. Again, the details are not important, but this is the chick embryo. There are 50,000 cells here. This is basically 3 millimeter wide, and the embryo is basically a single epithelial disc, 2-dimensional. And this process takes about 15 hours, in which cells will undergo motion at the embryo scale. So they will basically have a large long trajectories, if you will. Now, if you start looking at this process from an Eulerian perspective, a classical quantities are the velocities. You get basically plots of velocity fields over time. These features are frame dependent, meaning that if I just change a coordinate system, I can change all the topologies of these velocities, and we know that we want to go in Lagrangian coordinates. So what we can do, we can integrate this velocity and compute trajectories. So this is now trajectories that will tell if I start a patch of tissue at x0, after some time this patch is going to go somewhere else, x of t. F is just the trajectories, the map. And equivalently, you can compute the deformation gradient, which is going to tell you how an initial patch is going to deform into an ellipsoid. And if you want to visualize this, you can just overlay a Lagrangian grid that deforms with the tissue so that you have a sense of cumulative deformation along motion. An equivalent representation of df is basically the Cauchy-Green strain tensor. It's just df transpose times df. This Cauchy-Green tensor basically for any initial position of the embryo, basically say you have a Lagrangian coordinate, you map every possible patches of tissue with an x0. This quantity, this tensor is going to tell everything about how this patch is going to deform. It's going to tell you how much it will expand. It's proportional to the highest eigenvalue of Cauchy-Green, this red value. The direction of maximum stretching, the corresponding eigenvector, and similarly the least stretching direction, which is the other eigenvectors perpendicular to the leading one, and the corresponding eigenvalue. So now you understand that if you are in this position of the embryo, in Lagrangian coordinate, and you have a very high value of this quantity, cells that start at opposite side of this blob will separate distinctly. Okay, so now imagine that you have a ridge or a set of points where this largest eigenvalue of Cauchy-Green will be very high. That will mark a repeller, because that means basically that cells at the opposite side of this repeller will separate distinctly over time. Okay? So now you can compute these repellers on our experimental data. And what I'm going to show you, I'm going to show basically this field for increasing time intervals. Again, we have data for 12 hours in this dynamical system. I'm going to show you how repellers will emerge. Okay, so that's basically the Lagrangian coordinates. So this is basically initial embryo configuration. And you can see basically that over time there is going to be the formation of 2 repellers, 1 and 2, and which I'm going to describe their meaning in a second. So similarly, what you can do is computing attractors. Attractors basically what are regions in the final embryo configuration such that initial faraway cell will converge to at the highest rate. Okay? That's basically, this is an attractor from this same dynamical system, which is basically the chick embryo. And the set of repellers and attractor, we call them dynamic morphoskeleton because they are just units to morph or understand the evolution of this tissue. Dynamic because they evolve over time. They are not like stable or unstable manifold or steady dynamical systems, so they have their own dynamics. Okay, so basically what we did, we started from spatiotemporal velocity, and we compressed it into one repeller and two repellers and one attractor, just for a little bit of physics. So this repeller is going to split the extraembryonic region from the embryonic region. So there's basically a sharp demarcation of cells that will form the embryo and the ones that are auxiliary, that are extraembryonic. This attractor will be forming this streak. This is just the anterior-posterior axis of the embryo. And this repeller actually splits the anterior part and the posterior part of this streak. So this is basically a compartmentalization. So what we did, we started from velocities. We retained only objective or frame invariant deformations. We didn't consider all the possible deformation, but we considered deformation along trajectories, those that evolve and accumulate along cell path. They are all encoded in the Cauchy green. And then we said, okay, we are interested in regions where deformations are the highest, the attractors and the repellers. Okay? That's basically a compression. Okay, so now what I want to do, I want to show that whenever we rewrite these equations in Lagrangian coordinate, the advection, reaction, diffusion equation in Lagrangian coordinate, this tensor that we use, they pop up naturally. Okay? So assume now that simplest case, I have a confluent incompressible epithelium. I have a concentration, C bar is number of molecules per unit area, and I assume basically constant isotropic diffusion. Okay? So I have an advection diffusion equation plus other terms. You can put source, sinks, and other processes. And if you want to have this a little bit more visual, this could be this chick embryo. It's basically an epithelium. It's one layer of cells in the embryonic region. And then there is going to be right below an ECM, which co-moves with the epithelium. This is a layer that co-moves with the epithelium. And it's where cells are secreting ligands and ligands are moving so that cells can communicate with each other. Okay, so we learned, though, right before that if I just solve this equation, I'm going to get these solutions, the black ones. But what I want instead are the color ones, because those are the ones that the cells feel as they move. So we want to transform basically this PDE, transforming x into x0, using this diffeomorphism, which is just the trajectories. That's basically, I just want to apply a transformation which is spatiotemporal dependent, and rewrite this equation in the cell frame so that they can solve directly for these variables, which is what cells will feel as they move in these spatiotemporal gradients.
Sorry, I have a question.
Yeah.
For that. So you also have a dilution term, right, into the cell?
Yeah. You can add many other terms, but I want to focus on this. The diffusive flux is the only thing that will generate non-cell autonomous dynamics. Okay, let's see what this transformation does and what kind of tensor will emerge. Okay, but yeah, you can add everything here. You can add dilutions. Yeah.
And also suppose the diffusing dynamic and the growing dynamic there at 2 time scale.
The growing of cells or what?
Yeah.
Let me get into the simplest part. We basically encapsulated all the. There is a very beautiful review article by James Briscoe in which they show all the possible effects of on signaling about dilution, cell number density, etc. We modified this, but I'm just going to show one slide on that.
Okay. Thank you.
Yeah, it's premature, but you said it's incompressible because so you consider this fully in 3D because it tends to thin and thicken, right?
No. So no, this is basic. This is compressible. I just want to start with the simplest case, and then we account. Yeah, there is basically the divergence term there. Yeah. Okay, so when you start from this equation, what you get in the Lagrangian frame, now again we have an equation for Lagrangian coordinate. Remember, x doesn't know about cell trajectories. x0 is just mapping each patch of cells with a number, and that's basically this coordinate. So the first thing we notice is basically in the Lagrangian coordinate there is no advection. It's trivial because the Lagrangian coordinate system is moving with cells, okay? The other interesting observation is that here we started from an Eulerian diffusion tensor, which was isotropic, just d times identity, while in the Lagrangian frame, there is this new diffusion tensor that pops up that is equal basically to the molecular diffusivity times the Cauchy green inverse, okay? Where this Cauchy green is precisely what we learned in part 1, that was encapsulating the formation of the underlying tissue. So the one important message here is that in the cell frame, this is the dynamics that the cell will feel, and in the cell frame, the effective diffusion will be anisotropic, inheriting the anisotropy of tissue deformation along trajectories, and also will be space-dependent, naming that there are regions that will deform them more, and therefore you're going to modulate the effective diffusivity. So that's basically what I wrote here. And so in other words, in the cell frame, the effective diffusivity felt by a cell is going to be modulated by its deforming environment. Okay, how do we basically interpret this expression? Let's consider a linear 2D convergent extension. I compress in X, I expand in Y. I can compute trajectories and Cauchy green. And you see immediately, basically, that the Y direction expands by a value lambda, the eigenvalue of Cauchy green, which has this form. And the X direction compressed by 1 over lambda. Okay? And therefore, basically here, the y direction will play the role of the attractor because cells will go towards y in the x direction, and the x direction will be the role of the repeller because cells that start initially close will separate. Okay? Well, now D was just vector, so the diffusion tensor now was molecular D times C inverse. So you can just invert these entries, and you can get immediately that in X there is going to be enhanced diffusion, D bar times lambda, while in Y there is going to be reduced diffusion, D bar divided by lambda. Okay? So this is saying that basically the attractor will play the role of a diffusion enhancer, and the repeller will play the role of a diffusion barrier in the cell frame. You can basically visualize this. You can start with an initial condition. If you turn off motion, alpha, then this will just isotropically spread. But if you turn on alpha, you see that the diffusion of these ligands will be dominant across the attractor and reduced across the repeller. Okay, reduced across the repeller. Okay, so they will basically inherit the deformation. And again, this is just the Lagrangian coordinate. So these are patches of cells at their initial condition.
Let me ask you a question. So there presumably are cell divisions happening in some aspects of development. Those are left out at the moment?
I'm going to incorporate them later. So this is now number of morphogens per unit area.
Yeah.
If you want to go to number of morphogens per cell, you have to add the dynamics of cell number density, where you have division, ingression, etc.
But then there would be branching processes involved in your Lagrangian dynamics, presumably.
Yeah, but this is a mean field description. You're not really looking at each single cell.
But then the cells are increasing exponentially in time, or maybe at a slow rate. Yeah. There would be sources, at least in an Eulerian description.
Yeah.
What happens to those sources in Lagrangian perspective?
They will generate, so just with this, if you don't consider the cell number density dynamic, this would affect your divergence term. So that means basically if I have divisions, I'm going to generate a positive divergence. But we are going to account for this explicitly. Okay, so therefore basically in the cell frame, morphogenesis is basically changing the effective diffusivity via deforming the tissue. Okay? This is now just a trivial flow, but when you have just heterogeneous and steady flows, what do we do? Well, the result is already there because Cauchy Green does that for you. It remembers all possible deformation in space and time, right? So you can just extrapolate and say that attractors will always play the role of diffusion enhancer in the cell frame, and the repellers will always play the role of diffusion barriers. Okay, so let's, for instance, see a one-dimensional example, and then we go to the cheek example, which is more complex. So let's say that you have a source here that emits a signal, and then you have your Lagrangian coordinate, and let's say that you have a repeller here. Okay. So if I now let this, and then I have degradation and diffusion. If I turn off motion, what I recover after some time, I get this black curve, which is just an exponential decay, no motion. That's basically the stationary solution. But if I now turn on morphogenesis, I will get basically that the effect of this repeller is going to create a barrier to diffusion for increasing value of morphogenesis. So the stronger is the deformation, the more I create this sharp barrier. Okay? And remember, this is not advection, because in this coordinate, x0, cells don't move. Okay, this is just the non-cell autonomous term that is coming from the diffusive flux when I rewrite it in Lagrangian coordinates. Okay, so what we want to do now is say, okay, we have Cauchy Green in a two-dimensional compressible flow. There are 3 degrees of freedom. You can consider, for instance, the largest eigenvalue, which is basically the maximum strength of deformation. There's going to be the smaller one, another degree of freedom, and another degree of freedom would be the direction of deformation, the strongest stretching. Alternatively, you can consider the isotropic deformation and the anisotropic deformation. So the isotropic deformation will just be the determinant, the square root of the determinant of Cauchy Green. J is going to say at any point, if this patch of tissue is going to increase in volume, in area in this case, J is going to be greater than 1. And this increase of basically area will reduce the effective diffusivity in the cell frame. This is what you can get from the formulas I had before. And similarly, you can compute the anisotropic deformation, which is just the ratio of the 2 eigenvalues, which tells you basically how anisotropic is this ellipsoid. Okay, so this is going to tell you how the formation will anisotropically affect the effective diffusion. Okay, let's go now to our system. So this is now the cheek data. So this is the trajectories that you can see. These colors, these colored blobs will become clear in a second. But the only thing we can say already is that this is a complex flow, but if there is anything diffusing here, and with diffusion, I don't only mean molecular diffusion. This could be cytonins, transcytosis, or anything that you can model as a diffusive flux. Okay? I already know that if something is diffusing, repeller 1 and repeller 2 will block this diffusion, will act as diffusion barriers. This is a strong prediction because I don't know anything about the sources and the other mechanisms. And the other thing is that I know also that the attractor will act as a diffusion enhancer. Okay? What I want to do now, I just want to use this decomposition that I just said. So lambda, again, is going to tell you that this, you should interpret it as the maximum amount of deformation. When this is high, that means that in that location, basically, morphogenesis will affect effective diffusion the most. This instead is going to be the isotropic effect of deformations, which is just the area dynamic of patches of tissue, and this is the anisotropic deformation. And now I can play this over time because I have data over time. So at the beginning, deformation is equal to 1, no deformation, so log lambda is equal to 0. And after a little bit, you can see that you start forming structures, so you can understand when they form. These are the two repellers that we already know. They will tell you, for instance, that in these regions, the deformations will be affecting effective diffusion the most. Here you can say, for instance, that because I have positive j greater than 1, log j greater than 0, here I have the extraembryonic tissue that is expanding, and therefore here I'm reducing the effective isotropic diffusion in the cell frame. Here is the opposite. The tissue is shrinking because eventually it's going to ingress into the attractor, and therefore I'm going to enhance the effective diffusion. And here I can also read something else, which is that in this region there is going to be a lot of anisotropic deformation, so a lot of anisotropic effect on effective diffusion, and these arrows will also tell me the direction of this anisotropy. Okay, so what I want to do now is that, okay, those are very interesting observations. I don't know anything about the mechanisms yet, but I can always tell that just because the tissues are co-moving, so the cells are co-moving and the tissue is deforming, there is going to be this mediation on anything that is non-cell autonomous. Okay, and this basically comes from the fact that when you have the divergence of your diffusive flux, that divergence was before with respect to Eulerian coordinate, now it's going to be with respect to initial coordinate, Lagrangian coordinate. That's what does what does the job. So now I want to construct something very simple but visually effective to understand how do I quantify cell-cell communication. And we can identify something that is a fancy name but is trivial. It's called embryological time cones. It says if I am a cell at some particular region, x0, t0, and I start emitting a morphogen, and then I move, because everything is moving, here is very highly dynamic, you want to ask, after time t, what are the cells that I can reach? What can I reach after a certain time? Now you understand that basically, if there is static tissue, simple diffusion, this is the cell that is emitting, you're going to get a cone that is square root of dt. Nothing moves, simple diffusion. If you start having morphogenesis, you say that, okay, if I am now in a region of j less than 1 shrinking tissue, my effective diffusivity will be superlinear, for what I said before. So the cone is going to have a superlinear effect. If I have convergent extension, I'm not going to have a symmetric cone, but I'm going to skew it from the perspective of the cell. Okay, so the cell can be basically reaching this other set of cells. And it's very important that this is all in the Lagrangian coordinate. Here there is no confounding effect of motion. Okay? Okay, those are still trivial. What happens when you have basically the real data that we've seen before? What I'm going to do now, this is the video that I played before. And now I'm going to make this patch of tissue emit some signals, okay, at some particular rate. And we are going to basically see how these embryological light cones will evolve over time, okay? So this is basically the evolution of these three fields that I basically showed before. And let's see, for instance, there is a lot of information here. Let's go step by step. So first, remember that we had these repellers, okay? So look, basically this cone.
Sorry, 5 minutes.
Yeah, so this cone was basically, if there was no deformation, it would just be spherical, but you see the presence of this repeller is biasing this cone, avoiding him to propagate information non-cell autonomously in the embryonic region. So there is basically a barrier to diffusion here. Similar for this cone that is outside the repeller number 1. Another repeller is repeller number 2, and you can see that the repeller number 2 is actually preventing these two sources to communicate with each other. Okay? This is what you can get just knowing the deformation of the tissue that you can measure with a microscope. Another thing I want to do now, for instance, let's look at the dynamics of this blob. Okay? So for a very short time, the dynamics is such that after 120 minutes, 2 hours, the embryo didn't get the chance to deform. So lambda is still 0. Okay, so in the cell frame, this is still going to be a circle because deformation didn't have time to take place. But now let's look a little bit later. So you're here. Now this diffusing signal is hitting a region where anisotropic deformation matters, and it also tells you that this deformation is going to be enhanced. So this propagation is going to be enhanced in this direction from this vector field. Okay, and this is basically what the light cone is inheriting from that property. Okay, and now if you look at this region here, that's basically north of this point, you're going to see here that you start also having anisotropic effect in this region in the vertical direction, and therefore basically if you let this go, you can indeed see that this cone is basically highly affected by this anisotropic field. Or actually, you can predict the cone from an anisotropic field of the deformation. So basically, this is what we've seen. So morphogenesis-mediated transport, when I have basically deformation, diffusion, and these sources. And it's interesting to contrast this in the case of motion but no diffusion. If I just have motion but no diffusion, these cones will not be able to affect anything because propagating to other cells or expanding in the cone requires non-cell autonomous dynamics. While if you have diffusion but no motion, then you would just have isotropic growing cone with square root of dt, okay? And so therefore you can see that if you just contrast these two cones, you can see that when signaling is mediated by deformation, the reach that you can have is significantly different, okay? And this is actually what the cells are feeling. Okay, so basically, I will summarize. First, we show that compressing spatiotemporal flows into attractors and repeller via the Cauchy-Green tensor is a way to basically simplify spatiotemporal trajectories into kinematic units. Then we rewrote the advection reaction diffusion equation in the Lagrangian frame, and this Cauchy-Green tensor that we used in part 1 was actually the one that is mediating diffusion in the cell frame. And we also saw that these attractors and repellers are the regions where this Cauchy-Green is the highest. And therefore, they are the regions where the modulation of cell-cell signaling, non-cell autonomous, will be the highest. And in fact, you can show that attractors and repellers are diffusive transport enhancer and barriers. Okay? And then we showed this illustration, or this basically technique that allows you to predict, given the motion and the deformation of this tissue, if you have some plausible mechanisms, let's say sources, sinks, relay mechanism, etc., this is a way to test what cells can communicate with other cells. Okay? Yeah, I think I will. How much time do I still have?
Oh, you have 2 minutes.
Okay, so there is basically one recent observation with the Loic-Royer group at the BioHub. We found an interesting correlation with what I just saw. We found basically that the blob of cells that are transcriptionally identical, so they have the same cell type, after a repeller forms in between them, they will basically acquire different fates. Okay, this is just a correlation. It's just an analogy, non-analogy, basically a correlation, if you will. But it's interesting how it's going in the directions of what we just saw. So if there is a morphogen that is basically diffusing in this tissue, this morphogen will be blocked by this repeller. It's just an hypothesis. Maybe it's completely different, the reason why they're. And we found something similar also in the chick embryo with different collaborators, that basically repellers can basically help or bias cell-fate bifurcation for this reason. Then, of course, from here to understand cell-fate bifurcation is a different question. And So this goes back to the questions from David and Silke. So now I told you the dynamics of morphogen per unit area. Now if you encapsulated the effect of cell densities, where you have the effect of cell growth, cell division, dilution effect, again, there is actually a very beautiful review article from James Briscoe understanding and spelling out all these different processes of cell-cell signaling. We incorporated them here, and the effect of deformation is the same on the non-cell autonomous dynamics. And we can do this also on curved deformable surfaces using data that was acquired here. So now when you have an organoid or an organ that has deforming embryo geometry, we can have the same machinery and see the effect of deforming geometry on this process. And I'll stop here.
Thanks for the talk. I was wondering to what extent these ideas apply to intracellular signals versus extracellular, because you're assuming that the signal is being carried with the cells.
Yeah.
And can you comment on how much this would apply for an extracellular signal, for example?
These are extracellular. Because, so the idea is that, especially in this system, basically, the chick embryo secretes ligand, they're in the basal side, and then there is an ECM that co-moves with the cell. So it's not really inside the cell, it can diffuse, but of course it's very viscous, and people measured staining, fibronectin, and other markers of ECM, that the ECM co-moves with the tissue. So you see they're co-moving in this case.
Yeah, I see. So this applies to a situation in which the extracellular medium also moves. But I guess if you release it to a region without ECM, then...
Then you have to give me, if there is any drift, basically, of the ligands, we can incorporate it. If there is no motion, then you just don't have this correction.
Great, thanks.
Yes, very interesting concept. So what I didn't understand exactly is once you have your morphogen and you do this composition, etc., does this stay applicable if your morphogen gets coupled back to the mechanics? And if these things start to couple, what happens then?
Yeah, I mean, that's the future. But the idea would be this one, basically, that if you have now, so here you can add additional terms. You can start coupling the dynamics of Q. This Q is going to be really morphogen per cell as cells move. If you now are brave enough to attach here some terms that couples this with the tension in the tissue or whatever you can measure, then you can incorporate it in these dynamics. But I want to highlight that whatever we did here was basically kinematic. It's a prediction without assumptions on sort of these things. Yeah.
And maybe it's naive, but how is that different from what you'd expect just with advection, like you would put into advective terms?
Yeah. So it's very different. So the advection term in the cell frame, so actually let me go here. So the advection term, so the trick is all here in this divergence. Okay, so the advection is disappeared. If you basically have zero diffusion, it means you're just rearranging. But rearranging is gonna always have no expanding cones. If you want to infect your friends or your other cells, you need some non-cell autonomous terms. So, and the other thing is that, okay, a posteriori, you say, okay, now I solve the advection reaction diffusion, I project all my trajectories on the along trajectories, but it wouldn't be easy, I think, to predict that now, for instance, if I have this now, I don't know anything, but I can tell you already that these repellers will act as diffusion barriers. If there is anything diffusing there, I don't know that, but it's a sort of a good prediction that requires little. Only the motion, basically. Yeah.
Hi, Mattia. Nice talk. I was wondering how much what you've done is similar to what we do in fluid dynamics when we compute Lagrangian coherent structures.
Yeah.
To compute from the deformation matrix, we compute attract like a stable and
so the
unstable
first part,
manifolds.
yeah.
I think these are your attractant and repulsor.
These are basically used from fluid. The dynamic morphoskeleton is used from, is the same.
So the only thing is you substituted the deformation matrix with the Cauchy matrix, which is another deformation.
It's the same. Those are
the exact same ideas.
Yeah,
and people have been doing this in fluid dynamics where you put pollutants on one side and move it.
Yeah.
See that that those manifolds are basically barriers to transport.
Yeah.
Okay.
No, but all this machinery was not there. I mean, all this inclusion of cell dynamics.
Of course, you applied it to a different system. Yes, of course.
No, the machinery
absolutely.
is similar.
All right. Okay, thank you.
Just a quick question. Maybe you mentioned it, but I missed it. What's the Peclet number here?
Yeah, that's a very interesting question. Peclet is not what really matters. Okay, I can tell you the diffusivity that we used is 1 micrometer squared per second, which is consistent with what people observed in diffusing ligands from data. Velocities are micron per minute. That's basically the idea. But let me go back to this question.
Can we just continue, and the characteristic length scale?
It's, let's say, 1 millimeter. Yeah.
Can you just divide by 1?
Yeah, but
2 and tell us what the dimensionless parameter is?
But this is not the right dimensional parameter.
I would argue with that, because this is the parameter that tells you everything you need to know about the balance of diffusion and convection, right?
Let me see. I have it here. So if you have just uniform flow, the Peclet number would be non-zero. But here, the only thing, here the time scale is basically the Lyapunov of time, because what matters is really relative separation.
Right. It's
So
the variation of, right? It's the strain.
Yeah, but it's very
defines
different.
The relevant length scale, right?
Yeah, no, but this is it. So really, when you really want to compare if deformation is relevant, you say, okay, first of all, deformation, they should have time to manifest, to have basically appreciable deviation from Cauchy degree A12 identity, which is also what we saw before. That's basically one non-dimensional condition, which is FTLE times time interval greater than 1. And this is your question. So now...
Yeah, so I guess all I'm asking is, on the right-hand side, you have Peclet number. So what's that ratio?
This is not Peclet. This is basically, this is about 50 here.
Okay, I give up.
No, but this is not Peclet. This is Peclet.
And I'm asking, what is it?
1 micron, let's say 1 micron per second, let's say 2 microns per second, divided by L times L, which is, let's say, 1 millimeter, or 2 millimeters, whatever, and divided by D. And this is basically 1 micron squared per second. Okay, so basically we can get 2 times 1 millimeter. So this is, it's not super small. But
you said that the velocity is microns
per minute. Yeah, sorry. Yeah, it's micron per minute. But okay, so the Peclet can be small, but because the important thing is that you are not carrying, you are not advecting morphogen. That's very different. That's what you have when you say, okay, I have a source here, and there is a flow of cells that will transport this source. But if these cells are the same cells, this is only cell autonomous. This advection is purely cell autonomous. What matters here is instead the non-cell autonomous part. And if you do this calculation here, you get something that is on the order of 40. Do you understand? Because I mean, then when I show you, we can talk about this offline, but when I show you this is basically still moving. Everything moves. But in the cell frame, if you're moving but you're not spreading, it's like not affecting or infecting anyone else. So it's different from Peclet. I mean, let's say you have a uniform flow, very fast. Peclet would be very high, right?
Semantic material, you can define a velocity based on your Lyapunov exponent.
No, because if you have a constant velocity, you have no deformation. So you crank up Peclet as much as you want, but if you don't have relative deformation, this other parameter I showed you is 0. No, I understand, but that's not what Peclet is telling you immediately, because Peclet would be non-zero from a uniform flow.
No. Okay, sorry, if I can intervene as chair, I mean, if you define Peclet as a ratio of L squared over D to velocity gradient, thereby taking into account your worry about.
That's a
Is that
Peclet.
that's not, and it's not your omega 2 either?
In general, basically, nonlinear flows, you don't really have a general velocity gradient. That's basically the lapon of time tells you precisely how long does it take for a blob to deform by a factor E. And in this case, let's say it's 2 hours. That's what matters. Now, of course, this you can, if you have a linear flow, this is exactly the strain, the velocity gradient. But in a spatiotemporal nonlinear flow, this is exactly the number.
Maybe we should try to take the remaining questions, Erwin.
Yeah.
Maybe related to the other questions, can you somehow also think of this in terms of changing geometry, so a changing metric? And then my question would be, which part of the motion is because of the changing metric, and which part is simply because you advect things?
Well, I mean, when you're just, when you're just advecting in the cell frame, nothing happens. There is really no advection. So this is the only thing that remembers deformation via the Cauchy green. So now Cauchy green, I don't know if you understand your question good, but if you're in a curved surface, this Cauchy green is going to change because, of course, the stretching will depend also on your surface. And we did that basically in a follow-up, in one of the slides I didn't show. But whatever is making a difference here is really the deformation. This is basically unitless. It's just strain. And it's not immediately the same as Peclet. Because, I mean, the intuition is this. If I am this cell and I have, let's say, some concentration and I move very fast, the cell in front of me and before me, they don't feel anything unless I start deforming, relative deformation. So Peclet, I can crank it up. But the relative deformation is what matters for the non-cell autonomous part. Of course, you can then say, okay, if I have a linear flow, I can relate Peclet possibly I can relate Peclet to the lapon of time. But in general, it's really the lapon of time that tells you how long does it take for two cells to separate by E, for instance. Yeah.
I have a naive curiosity question. What does your formalism imply about the mechanism for the diffusion? Because you might imagine if there's some active transport of
Fichtean
cell
diffusion.
walls. Exactly, but so that's the relevant metric there is Euclidean distance in the Eulerian frame. You might imagine if there's something like active transport, the right metric would be something like, what's the number of cell walls I have to cross?
Yeah,
if that was the mechanism, would that change your conclusions?
Yeah, so if you would have that, then you should tell this information already at the Eulerian level, and then things should propagate. But here it's just accounting for the simplest case. Yeah, but.
Yeah. I see. So in your system, there are only one type of morphogen, or?
Yeah, this is for one morphogen. If you want to have more than one, you can see as a vector, and then possibly understand how they interact with each other. But the formalism is similar.
I see. Okay, thank you.
Since there seems to be 2 minutes left, I didn't understand one thing. You spoke of a you talked about a morphogenetic light cone. But I mean, a light cone normally is when I have a hyperbolic problem and I look at things like x plus t and x minus t. What you're talking about is more like, whereas for a diffusion, it's just, there's a similarity variable like x over root t, and it's spreading, but it's not.
You can just remove the light cone. First of all, there's also going to be one in the backward that tells you what are the cells that by this time can reach this cell.
Yeah.
But this is something very simple. You just, even numerically, what you can do, you can start emitting cells here. You have motions that is, the tissue is basically moving and deforming.
Right.
And then you want to ask, what are the cells that will be feeling C greater than a certain threshold?
So it's a threshold dependent notion.
Yeah.
All right, fine.
Yeah. This is because cells usually make decisions this way. But yeah.
Okay. Yes. Let's thank Mattia again for it.